one of the most prevalent questions that you'll encounter in physics dealing with forces, and that's a box on a ramp. And we will absolutely come back to this once we learn more about friction, once we learn about what happens if the box is moving down the ramp. So the first thing that I want you guys to do is I just want you to draw a free body diagram of the box on the ramp. And so go ahead and pause the video and draw yourself a free body diagram. If you have these two forces, you're off to a good start. Remember, the force of gravity pulls straight downward. And so even though the box is on a ramp, and if it were to move, it would move at an angle, the force of gravity is always, always, always straight down. And so it's not going to be pulled at an angle because the Earth pulls the objects to the center of the Earth. And then this is the normal force, and it appears whenever you have a surface. And it is perpendicular to the surface. And so that normal force will act on this line. And so it'll be perpendicular to the surface. Now, if I were to tell you that this box on a ramp does not move, then you automatically know that it is in equilibrium. Meaning the sum of the forces equals 0, which that means the sum of the forces in the x direction equals 0, and the sum of the forces in the y direction equals 0. So all of the forces are balanced. And so when I look at this, these forces are not balanced. So we'll have a force that goes up the ramp, or it would go this direction, sort of appear right here. That is going to be the force of friction. The force of friction is always parallel to the surface. So these are two notations that I want you guys to make sure that you understand. The normal force, this sign means perpendicular and is perpendicular to the surface, and the force of friction is parallel to the surface. So this means parallel. You should probably you might have learned that in math class. Okay, so when you do boxes on ramps, things get kind of tricky because we're not going to have our x and y go this way, because that means like two of our forces are in weird directions, and the box, if it were to move and we had our coordinate system set up like normal, that box is not going to move along one of the axes. And so that's going to make things complicated later on. When we deal with boxes on ramps, we're going to rotate our coordinate system so that one of the axes is parallel to the ramp and the other axis is perpendicular to the ramp. And then that'll make things a whole lot easier. And so I'm going to come in here to my free body diagram, and I hope you guys are doing this along with me. You're taking some notes. I'm going to come into my free body diagram, and I'm going to sketch in this axis and this axis. So now I only have one force, the force of gravity, that is not along one of my axes. Now, you can continue to call these x and y, but that kind of gets a little bit confusing because they're like, which one is x and which one is y? So I'm going to call this axis now, I'm going to call it the parallel axis, and I'm going to call this one the perpendicular axis. And so while we could sum our forces in the x direction, and we can sum our forces in the y direction, we now can, instead of saying x, we can sum the forces that are parallel to the ramp, and then we can sum our forces that are perpendicular to the ramp. Okay. Now, because it's in equilibrium and the total sum of the forces is going to be equal to 0, we can say that the sum of the forces parallel to the ramp, if this box does not move, it's in equilibrium, that's going to be equal to 0. And the sum of the forces in the perpendicular direction, that's going to be in and out of the ramp this way, that will also equal 0. So when I look at my ramp. I'm going to sum the forces. Let's do parallel first. Okay, so if I look at this parallel coordinate system, the force of friction is all in the parallel direction. And I'm going to call down the ramp positive, and you'll maybe figure why I do that later. So down the ramp is going to be positive. So I get this force of friction is going to be negative. So I get a negative force of friction. And then this force of gravity, we could twist it like this and it might start looking a little bit more familiar. This force of gravity is in the x direction, or the parallel direction, and the y direction, the perpendicular direction. So we will have the force of friction is going to be added to the force of gravity parallel to the ramp, and that's going to be equal to 0. So we could just say that the force of friction then is going to be equal to force of gravity parallel to the ramp. And we'll come back to what this actually is in a second. When I sum the forces in the y direction, or the perpendicular direction, remember that's what I'm calling it, I get the normal force. And I'm going to say that out of the ramp is positive. So I get the normal force is positive minus the bit of this force of gravity that's going to be in the perpendicular direction. And remember, I'm in equilibrium again. The sum of the forces equals 0, so this is going to be equal to 0. So I can write that the force of gravity perpendicular equals the normal force. Okay, so how do I find this, and how do I find this? How do I find these parallel and perpendicular components? Because things are starting to look a little bit crazy here. When you are given this problem, you'll be given the ramp angle, most likely. So let's draw this in, and let's just call this, let's say that it has a ramp angle of theta. Okay, so the question is this theta or is this theta? And I don't have a really good trick for this, and I wish that I did, but the triangle that we're going to draw, we are going to drop a perpendicular line or a parallel line to the parallel axis. We're going to drop that straight back to the line that the normal force is on. So the normal force, we're going to drop this straight back parallel to the ramp, and that is going to start our triangle. Okay, so the triangle that we have here, this is going to be our force of gravity that's perpendicular to the ramp. And this is going to be the force of gravity that is parallel to the ramp. Just like the x for FGX and FGY. So the angle, theta, is the angle that this triangle encloses, this one. So remember, you take that normal force and you sketch it all the way back, and then you drop a perpendicular line in from your force of gravity. Then all we have to do is find the sides of our triangle. Remember, I told you I write SOHCAHTOA on all of my papers. So the sine is the opposite over the hypotenuse. So the FG parallel is going to be my sine side. So the sine of theta is the opposite FG parallel over my hypotenuse, which is the force of gravity. So FG parallel, if I multiply both sides by the force of gravity, is the force of gravity times the sine of theta. Now remember, the force of gravity is just the mass of the block times the gravitational field strength times the sine of theta. Once you figure out one of the components, the other component, the perpendicular component, is just going to be, instead of the sine, it's going to be the cosine. But I'm going to walk through that one real quick. So my FG perpendicular here is the adjacent side. So the cosine of theta here, it's right next door. Cosine of theta is the adjacent, FG perpendicular, over the hypotenuse, the force of gravity. So that gives me the force of gravity perpendicular is Fg cosine theta. And so when we come back into here, if I ask you what is the force of friction, well, that's just going to be equal to Fg parallel. So the force of friction is mg sine theta. And if I ask you what is the normal force, well, the normal force is just the perpendicular part. So the normal force is Fg or mg. Remember, the force of gravity is just the weight, which is the mass times the gravitational field strength. So that's going to be mg cosine theta. Okay, I'm going to have you guys do a problem like this for your work for today.